Hello, everyone, and thanks for taking the time to attend this 5-minute talk. My name is Danny Shapiro. I'm a software architect and a researcher at Dell Technologies City office. I work on our HPC machine learning platform out of Europe office of the CTO research organization, where we develop innovative solutions and conduct strategic studies that are easy to scale and easy to ship to production to business units. Today I'm going to tell you about our distributed HPC machine learning platform, developed by me as an integral part of LifeChamps project, as it is aligned with our data management strategy, and now actively being used by project consortium developers to develop machine learning models for healthcare. I'm going to tell you how our platform helps LifeChamps to overcome the scalability challenges that arise as models and datasets continue to grow and how our HPC machine learning platform was created to address these challenges. We've got a lot to cover, so let's get going. LifeChamp strives to improve the quality of cancer patients by leveraging the power of AI ML developed by Dell Technologies HPC platform. The project is founded by European Commission, composed of 15 partners across Europe. The number one deliverable of LifeChamp's Horizon 2020 project is production-ready HPC machine learning platform, followed by a workshop to onboard developers and data scientists as quickly and as easily as possible. I started the workshop with the developer guide for a quick ramp-up, followed by a walkthrough of the platform landscape. For this job, we used our HPC Customer Solutions Center located in Frankfurt. To simplify things, I start with the basics. High performance computing, or HPC, is aggregation of computing power to solve problems which are either too large to standard computers or would take too long. It also referred as supercomputing for this reason. It enables the simulation or analysis of huge volumes of data that would otherwise not be possible with standard computer. The common challenges with high-performance computing is that you're producing or processing more data than your infrastructure resources can handle, and you have to wait for weeks or months to see the results, which typically delays the innovation and slows down the research. You can think of high-performance computing system as a group of computers, which is called cluster, and each computer in the cluster is called a node. Each unit in the cluster has an operating system, a GPU, storage, and networking capabilities for the units to talk to each other. A smaller cluster can have 16 GPUs with 4 GPUs per node, helping us to solve the problem much faster. Now let's put it all together for our HPC workload. Our cluster was developed with the developer in mind, using the following technologies. Dell Technology servers coupled with NVIDIA GPUs. Bright Cluster Manager. Slurm the scheduler. Message passing interface. Environment modules for development flexibility. Anaconda. Top leading machine learning frameworks. Harvard. A developer can use any top machine learning languages out there. Models and datasets continues to grow from gigabytes, terabytes, and even petabytes. At that point, there is really no way to feasibly process all the data on a single machine or a single GPU. And so, parallelizing network becomes a critical part of the performance of the training process. What if I told you you could write your code using any programming language out there as if your code is running on a single GPU without any care of underlying infrastructure? But when you execute your code, the cluster will distribute and then aggregate the execution across all the nodes. De facto, parallelizing the execution of the code across all the nodes and their GPUs, thus shortening the execution time in factor of number of the GPUs in the cluster. Up until recently, it was not a simple task to develop unless you wrote your code to distribute and then aggregate the results across the nodes and the GPUs in the cluster. Our solution renders this development effort obsolete, thus reducing the development time and complexity, and makes the process more cost-effective. To summarize, let me show you a quick demo of how it's done. It actually runs TensorFlow MNIST PY. Okay, so it's just a TensorFlow script that trains MNIST network. But the thing I would like to achieve here is I would like to run it on 4 GPUs, meaning I would like it to be distributed on 4 GPUs and not on only one, parallelized on 4 GPUs, distributed and then aggregated back, and the results written somewhere. Okay, that is what I'm going to show you right now. Uh, 4 GPUs here, as you can see, P100 SMX2. Now I'm going to execute the Slurm job, which is TensorFlow MNIST. Okay, this one using Slurm. Through Slurm, what I expect to happen, I expect the utilization of the GPU to. We basically submitted a job to job number 82 to Slurm, because as you can see, Slurm, and we should be seeing stuff happening here. Okay, see, it's allocating memory, starting to train. You see, okay, all of the 4 GPUs are working simultaneously. While, because it's quite a large data set, it has to download it first and then train it. But relatively fast because it's 4 GPUs. Way faster than it's going to be a factor of 4 if you're just important for us. Basically, the graph that has been created, you can see quite FT1, but that's the result of the run. I invite you to check us out on our Intel Dell page, Confluence page, LinkedIn, or by email. I would love to talk to you about what we're doing. Hope you found this talk interesting. Thank you very much for your time.